Hello everybody, this is Homer White back again with part 3 of the 10th chapter of our course. We're working on tests of significance. In part 3, we're going to take a little closer look into why safety checks are an important part of inferential procedures, both confidence intervals and tests of significance. We're also going to talk about the types of error that can be made when you perform a test of significance, the ways in which your conclusion can be wrong. Always remember to make sure the necessary packages are loaded. Let's now talk about the importance of safety checks. So we've been using the t-statistic in questions involving means. We've been using the t-statistic to build confidence intervals for a mean, for example. We've also been using it to get p-values in tests about one mean. And we've been doing the same for the difference between two means and a mean of differences. The t-statistic appears to be pretty important in all of these procedures. We know some things about the t-distribution from statistical theory. It turns out that if you sample n items at random from a population, and if that population is normally distributed, so a density plot for it would look exactly like the bell curve, then the t-statistic itself, that's the sample mean minus the mean of the population divided by the standard error for the sample mean. That t-statistic, as a random variable, has exactly a t-curve distribution with degrees of freedom equal to 1 less than the sample size, so equal to n minus 1. Let's remind ourselves what these t-random variables are like. There's a whole family of them, one for every possible degree of freedom, 1, 2, 3, and so on. We can use a manip app to explore their shapes. When we open up the app and look in the plot window, we see a graph for the density curve for a t-random variable with degrees of freedom equal to 1. If we click on the wheel, we see that we can vary the number of degrees of freedom. We can also show a picture of the standard normal curve, the curve with mean 0 and standard deviation 1, to compare with these t-curves. Let's ask for one. So at 1 degree of freedom, we see that the t-curve is symmetric, centered around 0, but somewhat different from the standard normal curve. It has fatter tails. It's also somewhat flatter along the sides. Let's increase the degrees of freedom just a bit. At 2 degrees of freedom, we see that the t-curve is somewhat closer to the standard normal curve. Still symmetric around 0, but still with heavier tails. Let's keep on increasing the degrees of freedom to 3, to 4, to 5, 6, 7, 8, 9, 10. It appears that the higher the degrees of freedom, the closer a t-curve is to a standard normal curve. Let's move the degrees of freedom up to, say, 30. At this point, I can barely tell with my naked eye the difference between a t-curve with 30 degrees of freedom and the standard normal curve. At 100 degrees of freedom, I don't think anyone could tell a difference. So what we've learned is that when the sample size is large, the degrees of freedom will also be large, because it's 1 less than the sample size. And the t-curve at these large sample sizes will be approximately a standard normal curve, a perfectly bell-shaped curve with mean 0 and standard deviation 1. So, if the population is normally distributed, the t-statistic will be exactly a t-random variable. But what if the population is not normally distributed? We know that in practice, the population hardly ever is going to be perfectly normally distributed. Well, as our explorations have shown us, if the sample size n is large, then a t-random variable will be approximately the standard normal 0, 1 random variable. Also remember the central limit theorem, which said that at large sample sizes, x bar is approximately normal. And therefore, if you take away the expected value of x bar and divide by its standard deviation, then the resulting standardized random variable will be approximately normal, but with mean 0 and standard deviation 1. Now let's think about the t-statistic, which is x bar minus mu divided by the standard error. Now remember that the standard error is an estimate of the standard deviation of x bar. It's simply the sample standard deviation divided by the square root of n, the sample size. That estimates the population standard deviation sigma divided by the square root of n sample size that makes up the standard deviation of x. Well, at very large sample sizes, the sample standard deviation should be pretty close to the population standard deviation, and therefore the standard error for x bar should be pretty close to the standard deviation for x bar. The upshot is that the ratio that makes up the t-statistic as a random variable should behave a whole lot like this ratio here, this standardized ratio. If the standardized ratio is approximately normal 0, 1, then the t-statistic will also be approximately normal 0, 1. So, we've been able to argue that at large sample sizes, the t-statistic will be approximately normal, with mean 0 and standard deviation 1. But we also have seen with the t-explore app that at large sample sizes, the t-random variable is approximately normal, 0, 1. We can then conclude that at large sample sizes, the t-statistic has approximately a t-random variable distribution within -1 degrees of freedom. So, if the population is exactly normal, the t-statistic is exactly the t-distribution within -1 degrees of freedom. But even if the population is not normal, at large sample sizes, the t-statistic will still be approximately the t-distribution within -1 degrees of freedom. So as long as the sample size n is large, it's going to be okay to use these t-curves to make confidence intervals for mu and to approximate p-values in tests about the population mean mu. And you can do this no matter what the underlying population looks like. This is all if the sample size is large. But what if the sample size is not large? Well, if the sample size is small and the population departs from a normal curve in some important way, for example, suppose that it's very skewed, or that some subgroup of it lies way out from most of the rest of the population so that you have some sort of outlier group in the population, then there could be problems. The t-statistic might not have a probability distribution that's a lot like a t-curve at all. We can investigate the extent to which this happens by looking at another app. It's called T-Sampler. So we have applied T-Sampler to the data frame ImagePop, the imaginary population of 10,000 people. Remember that one of the variables in ImagePop was the annual income of each person in dollars. And we're looking here at a density plot of incomes in the ImagePop population. As you can see, it's a somewhat right-skewed distribution. We see that we're set at sample size 2 right now. We're going to take random samples of size 2 from this population of incomes. Once we've built up several different samples, each with its own t-statistic, we're going to see a density curve take shape in the plot window that estimates the distribution of the test statistic. So let's click on the sample size indicator repeatedly, and let's make this process start to happen. If you go over into console, you see that for our first sample of size 2, the test statistic happened to be 0.341. Second time we tried it, the test statistic was minus 0.493. Looking over in the plot window, we see that now we have a density curve taking shape. It's based so far on only 2 t-statistics. The first t-statistic we took is indicated by this little hatch mark, and the second is indicated by the hatch mark and the blue dot. The blue dot will always occur over the most recent t-statistic that has been recorded. These are the only two t-statistics in our group so far, and so we have these two humps over each of them that make up the density curve at this point. Let's continue to take more samples of size 2, and thus get more t-statistics, and get a better estimate of what the distribution of the t-statistic looks like. You know, I think I'm going to stay at this for a little while, so you might want to go watch a YouTube video or something while I finish up. Y'all ready for this? Okay, we're back now, and as you can see from the rug on the horizontal axis, it appears that I've taken quite a few samples of size 2, computing the test statistic each time, and the density plot that you see offers a pretty good approximation of the distribution of the test statistic at sample size 2 from this very skewed population of income. If the underlying population had been exactly normal, then we know that the t-statistic would have behaved exactly like a t-curve with 1 degree of freedom. If we push the Show t-curve button, we'll get a t-curve with 1 degree of freedom to compare. And as you can see, the difference is quite substantial. The actual distribution of the test statistic at sample size 2 from the skewed population is right skewed as compared to the very symmetric t-curve with 1 degree of freedom. Let's also think about our conventions for what constitutes an unusual or an unusual value. By convention, we've tended to say that a value is unusual if it's more than 2 standard deviations above or below what's expected. So we might consider a t-statistic value to be unusual if it turns out to be more than 2 or less than -2. Let's show some vertical lines that will represent the borderlines between being surprised and not being surprised by a given t-statistic. You might also notice that all of the times that it has gone outside, it has been above 2. It's never been below -2. Now, what might happen if we tried a larger sample size? Let's try sample size 30. And again, let's take a break while I take a few more samples of size 30. So welcome back. Notice that I've taken quite a few samples of size 30, computing the t-statistic each time. The blue density curve that represents our estimate of the distribution of the t-statistic is much more symmetric this time, and much more similar to the theoretical t-curve with 29 degrees of freedom that you see there in red. Also notice the percentage of times that we got surprisingly large or surprisingly small values of the t-statistic. Here we got a t-statistic above 2. Here we got a t-statistic below 2. Notice that this time there's surprises on either side. And notice also the percent of surprises, 5.349%, is a lot closer to what you might expect if you were working with something that's normally distributed. And in fact, since the theoretical t-curve at 30 degrees of freedom is pretty close to a normal curve, then you get approximately normal curve behavior for the t-statistic. So about 95% of the time, no surprise. About 5% of the time, surprisingly large or small values for the statistic. So the moral of the story seems to be that at large sample sizes, it doesn't really matter much if the population is skewed. And one would find the same things if it had an outlier group. Doesn't matter much. t, the t statistic is going to have approximately t distribution within -1 degrees of freedom. But at smaller sample sizes, when the population is skewed or has an outlier group, then the distribution of the t statistic is so different from the corresponding t-curve with the right degrees of freedom that you really can't rely on inferential procedures that are built from that t statistic. And so when our sample size is not large, say if the sample size is less than 30, then we need to check our sample. We need to make a histogram of the sample, or a density plot of the sample, or a box and whisker plot of the sample, something that will give us an idea of the distribution of the sample. Because if the sample shows skewness or outliers, then probably it does so because the population has those features too. In that case, t-test GC might not be reliable. So this is just one indication of why those safety checks that we perform early on in a test of significance are so important. Now let's talk about the types of error that you can make in your decisions and conclusions in a test of significance. Remember confidence intervals? They were actually designed to be wrong sometimes, as you'll recall. Remember that 95% confidence intervals for a population mean mu are designed to fail to contain mu about 5% of the time in repeated sampling. And in general, a 100 times 1 minus alpha percent confidence interval will fail to contain mu about 100 times alpha percent of the time in repeated sampling. In the same way, tests of significance are designed to be wrong a certain percentage of the time. They do not always make the right decision about the value of the population parameter. Here are the types of error that you can make. There's two things you can decide to do in step 4 of a test of significance. You can decide to reject the null hypothesis, or you can fail to reject the null hypothesis. Those are your decisions. But also, there's two ways the world could be. It could be that the null hypothesis is true, and it could be that the null hypothesis is false. Either the population mean mu has the value that the null believes it has, or mu does not have that value. Now, if the null hypothesis is true, and based on your sample data you decide to reject the null hypothesis, then you've made an error. You'll never know it because you don't know and never will know the true value of the population mean. But you've made an error, and it's called a type 1 error. On the other hand, suppose that the null hypothesis is actually false, but you don't reject the null hypothesis. Then again you've made an error, and it's called a type 2 error. So a type 1 error is rejecting the null when it's actually true, and a type 2 error is failing to reject the null when it's actually false. Here's some more statistical theory. If the null hypothesis is actually true, and your cutoff value for a test is set at alpha equals 0.05, then a well-designed and trustworthy test of significance will commit a type 1 error about 5% of the time in repeated sampling. And in general, if the null hypothesis is true all along and your cutoff value is some number alpha, then a well-designed test of significance will commit a type 1 error about 100 times alpha percent of the time in repeated sampling. So if you had a looser cutoff, say alpha equals 0.10, and if the null were true all along, and if you took sample after sample from the population, then about 10% of the time you would incorrectly reject the null hypothesis. If you don't believe it, then try this Manipulate app. So here's how the app works. The density curve in red that you're looking at is a density plot for the weights of some population of males. Notice the vertical line, mu. The mean weight of all the males is 170 pounds. Also along the horizontal axis you see mu naught. Mu naught is the null hypothesis's belief about what the mean of the population is. So at the moment, the null hypothesis is true. Mu naught is the same as mu. It's 170 pounds. Notice that we have a sample size here set at 10. If I were to take a sample, I would take a simple random sample of size 10 from this population of all males. Let's do so. The light blue colored histogram represents our sample. The blue dot is the mean of the sample. The yellow line is a 95% confidence interval for mean. Notice that the yellow line almost extends to mu naught, but doesn't quite. So the null hypothesis's belief is just outside of the 95% confidence interval. We therefore know that the p-value for this test is going to be less than 0.05. We're going to be rejecting the null hypothesis this time. When we look down into the console, we see this result recorded. The null is going to be rejected, true. So far, we've rejected the null once. We've only tried one sample, and so 100% of the time, we have rejected the null. We've made a type 1 error because the null was actually true. The mean of the population really was 170. But we happened to get a sample of size 10 that contained some fairly large weights. And so our sample was unlucky in a sense and caused our type 1 error. Let's try another sample of size 10. This time, sample mean was somewhat closer to 170. The 95% confidence interval contains the null's belief mu naught of 170. So our p-value will be bigger than 0.05. We won't be rejecting the null, and in fact we did not if you look down in the console. So this time we did not make a type 1 error. Let's try more samples. Another sample of size 10, and another, and another, and another. We see another case in which the confidence interval did not contain mu naught. We'll be committing a type 1 error again. As you go along, you'll notice that most of the time, you don't commit a type 1 error. The null hypothesis is true, but most of the time your confidence interval contains mu naught, and the p-value is bigger than 0.05, and you fail to reject the null. We've done this a few times. Let's check down in the console to see how things are going. So in our last sample, we got a p-value bigger than 0.05, and we did not reject the null. We've done 29 samples total so far, and rejected the null only once in those 29 times. And so the percentage of times that we've committed a type 1 error, falsely rejecting the null, is 3.4%. Let's try it a whole lot more times. Instead of just going one at a time, why don't we go 1,000 at a time? And at the end of my 20,000 samples, I committed a type 1 error 1,013 times. That's an error rate of 5.1%. In practice, things are difficult. You don't want to make errors. You'd like to cut down, for example, on the chance of a type 1 error. So you might set the cutoff value alpha very low. If alpha is set very low, it's going to be hard for p-values to be lower than it, and so you won't very often reject your null hypothesis. Therefore, you're not so likely to falsely reject the null. But then, if the null hypothesis actually is false, and you're making it hard to reject the null hypothesis, then you're making it more likely that you're going to commit a type 2 error. And if you want to cut down on the chance of type 2 errors, in that case, you might want to make it easier to reject the null hypothesis so that you'll more often reject the null when the null really is false. Well, to make it easier to reject the null hypothesis, you should set your cutoff value alpha high. But then, when the null hypothesis is true, type 1 errors are going to become more likely. Life is hard, and then you die. The only way to make type 1 errors unlikely and type 2 errors unlikely as well at the same time is to set alpha very low and take a really large sample. But large samples are expensive and time-consuming. When thinking about type 1 and type 2 errors and understanding the logic of test of significance in general, it can be useful to think in terms of the criminal trial analogy. A test of significance is like a criminal trial in which only the prosecution presents evidence, and for one reason or another, the defense decides simply to rest its case before making it. In this analogy, the null hypothesis in a test of significance is just like the defendant's plea of not guilty, and the alternative hypothesis is just like the prosecution's claim that the defendant is guilty. In a test of significance, there's a parameter whose value we do not know and will never know. In a trial, there's the truth about the situation, whether or not the defendant actually committed the crime. And that we'll never know for sure. In a test of significance, a test statistic gives a numerical summary of how much evidence the data is providing against the null hypothesis. Large test statistics tend to provide lots of evidence against the null. So the test statistic is essentially like the prosecutor's evidence against the defendant in a criminal trial. In a test of significance, there's a p-value. The chance of getting data like what we've got if the null is really right. Well, the p-value is a lot like what the prosecutor might do in closing arguments. The prosecutor might say, look, suppose this defendant did not commit the crime in question. Then what are the chances that we would find such things as the bloody glove in the back of his car, the defendant's DNA all over his clothing, etc., etc. The prosecutor is essentially asking the jury to compute a p-value. And if they find that p-value to be low, to convict the defendant. Therefore, the decision that one makes about the null hypothesis in a test of significance is like the jury's verdict in this situation. And just as we reject the null only when we have very strong evidence against the null hypothesis, so the jury is instructed to convict the defendant only if the defendant is seen to be guilty beyond a reasonable doubt. Test of significance can go wrong. You can commit a type 1 error. So that's incorrectly rejecting a true null hypothesis. In the trial, it's just like incorrectly convicting a person who is in fact innocent. In a test, you have the possibility of type 2 errors. So that's failing to reject null hypotheses when in fact they are false. In the trial situation, that's just like letting the guilty person go free. Thank you for listening.